From our daily life experiences, we intuitively know that it is much easier to open a door if the hand is not too close to the hinges. Or you might have wondered why doorknobs are not next to the hinges. The answer to all these thoughts lies in the concept of moments. Before we dig into the definitions, let us perform a simple experiment. Try to push the door close to the hinges. What do you observe? Now, try to push as usual near the doorknobs. What did you observe this time? The closer you push to the hinges, you had to exert more effort or larger force. And in the second case, you could rotate the door with little effort. In other words, the larger the distance from the axis of rotation, the minimum force is required, and vice versa. Does it also depend on the angle at which force is applied? The answer is yes. One cannot rotate the door if one applies force as shown here. We can compactly put our observations into a mathematical formula. The quantity torque or moment of force is defined as the cross product of radial line R and force F. The door rotation example can now be seen in terms of equation of defining torque. Torque is a vector quantity. A torque that tends to rotate the object in a counterclockwise direction is positive, while a torque that tends to rotate the object in a clockwise direction is negative. The example of a wrench that's loosening a nut can neatly summarize the core concepts associated with torque. Take a look at this diagram. Now, the next thing is to briefly discuss the effect of two torques with equal magnitudes acting in opposite directions on an object but not through the same point. The quantity called couple produces rotation and is in action whenever we open a doorknob, open or close a tap, wind a watch, or use the steering wheel. Next, we need the concept of static equilibrium. The word equilibrium intuitively hints at balance, and static, as expected, means the absence of motion. There are two conditions to say a rigid body is in static equilibrium. First, the net force is zero. Second, net torque is zero. Why both conditions? The second condition is needed because a body can be out of equilibrium even if the net force is zero. Take a look at this block in all three figures. In the last case, the body can rotate even though the net force is zero. Given that we know the concept of force, torque, and static equilibrium, can we appreciate our body's robust mechanics, particularly the ankle joints? For demonstration purposes, we will assume a simple model of a foot and ankle operation where the foot pivots as a single structure about the single pivot in the ankle. This seemingly simple model will help us to explore the operation of the ankle joint and draw some interesting conclusions. When you stand on tiptoe, your foot pivots about your ankle. As shown here, the forces on one foot are an upward force on your toes from the floor, a downward force on your ankle from the lower leg bone, and an upward force on the heel of your foot from your Achilles tendon. Now, let us put some numbers here to give you some idea about the magnitude of the forces. Let us assume the person's mass is 61 kg and the sole of the foot makes an angle of 25 degrees with the floor. We can ask how much tension is in the tendon. Does it exceed the person's weight? What is the magnitude of the force in the ankle joint? First of all, let us simplify the view of the forces applied on the foot. Forces are here applied at different points and the foot is pivoted around the ankle. Let us apply the concept of the static equilibrium, which demands the net force and the net torque must be zero. Three forces act on the foot. The force of the floor and tendon have only a y component. There must be no net force along either the x or y axis. The force from the floor is equal to the person's weight, which is around 600 Newton. This acts at a perpendicular distance of 15 cm from the pivot and it is directed upward. The force from the tendon is simply the tension in the tendon. This force acts at a perpendicular distance of 5 cm from the pivot and also directed upwards. The final force is the force at the pivot, the force in the joint, which we denote as F joint. This is the force with which the bones of the upper leg press on the bones of the foot. This force acts at the pivot and contributes no torque. It must be downward to balance the two upward forces. The foot is in a static equilibrium, so it experiences no net force and no net torque. The force at the pivot contributes no torque, so the torque condition reduces to solving this equation, which yields the tension as the 3 times the person's weight. Let us now look at the net force zero condition for static equilibrium. The equation for the force in joint yields a number which is 4 times the person's weight. Now, Do these numbers make sense? Yes. If you remember opening the door example, you had to exert less force when the perpendicular distance from the pivot or hinges was large. But the opposite was true for the case where you moved closer to the hinges. The same logic applies here. The force of the tendon acts closer to the pivot than the force of the floor. So we expect this force to be larger than the person's weight. Our muscle and bones may look fragile compared to many things, but its design is indeed remarkable.